All right, so let's reiterate. The problem we're being asked to consider is you decide that you're going to save $500 a month with the goal of eventually buying a car. So at some point in the future, you'll buy a car. You're going to take $500 and you're going to bring it to the bank or someplace like that that's agreed to pay you interest. So I started with this let statement. I said let B sub n be the balance in the account at the beginning of month end. Okay? And then additionally, we're going to say something about the bank we're going to. They compound continuously at 3% annual percentage rate. So they've decided to compound continuously. All right? So let's just start to write out what's happening, and then eventually you're going to notice a pretty famous series of here. Okay? All right, so what would happen here? We'd go to the bank, and the beginning of the first month, we would show up, and we deposit $500 in the bank. So just in case you don't know, the bank will not give you any interest on the first day you drop off this money. They're going to wait a month before they pay you anything. So we start off month one with $500, and then that's it. All right, let's get to the beginning of month two. Here's where things get a little bit interesting. The bank says, hey, thank you for leaving that money with us all that time. We're going to pay you the interest that we promised. So we're going to take $500, and you're going to multiply it by something. Now, let's just remember what compounding continuously means. Compounding continuously means that our investment grows according to this formula. P equals P initial, P sub 0, e to the RT. Where R is the rate, T is going to be time in years. Okay, this is the rate as a decimal. And P0 is the investment, whatever we're investing. So you could think of this problem like an investment problem, if you like. All right, so if we use that formula here, $500 is our P0. That's what we gave to the bank a month ago. They said we'll give you 3% interest, so that's 0.03, for the number of years you've left the money with us, which so far has only been 1/12 of a year. Now, don't forget, you're also going to drop off another $500 because you've made a promise that every month you're going to go to the bank and put $500 in this account. So there you go. So that's what you have there. All right, let's keep going. All right, so beginning of month 3 comes along, and here's what happens. That first $500 you deposited at the beginning of month 1 multiplied one time, and now this whole amount of money here, this whole value, is going to get interest. So I'm going to write it a kind of a cumbersome way, and then we'll write it a more efficient way. So this amount of money here, that whole amount of money, again, gets multiplied by this, e to the 0.03 times 1/12. And the reason that's happening is this investment of dollars, right, has been in the account for another month. So that amount of money gets multiplied by this. This $500 over here now finally earns some interest from me. It's only been in there 1 month. So it's going to get $500 times e to the 0.03 times 1/12. And then lastly, you've committed to deposit another $500. Just to reiterate, this whole number here is acting like that P0. That whole number is going to get is really my initial investment, and it's getting multiplied by e to the RT again. It's getting multiplied by that term. That's where this comes from. Okay, so let's write this more compactly. So I'm going to write B sub 3 equals, and if you notice, these two things are the same. So I can write 500 times e to the 0.03 times 1/12 as an exponent squared. Let's keep going. The remainder of this is the same. Okay. So maybe we'll do one more step, and then after that I think we'll be ready to generalize this into like something with B sub n rather than with specific numbers. So let's pretend we're going to go to the beginning of the 4th month. Okay? And what's going to happen now is that this money here, that's that first $500 I ever deposited, it's got interest from me twice. It's going to get interest from me again. So this thing will turn into 500 times e to the 0.03 times 1/12 to the third. And then that next term will be 500 times e to the 0.03 times 1/12 squared. This money will turn into 500 times e to the 0.03 times 1/12. And then lastly, I've promised to deposit another $500. What you're seeing in each case is that this money, for example, had a chance to earn interest again. So that's why the exponent went from 2 to 3. This money had a chance to earn interest again. It only earned interest 1 month. Now it's been earning interest for 2 months. This money finally got its first chance to earn interest. So that's why there's really this thing to the first power. I didn't bother to write it. And then this last $500, well, that just got deposited. So it doesn't get any interest yet. I have to wait till the beginning of the 5th month. So if we look carefully at this, we might be able to see a pattern. So, for example, if you look at B3, the highest power I see is 2. If you look at B4, the highest power I see is 3. We go back to B2, the highest power I really saw here was a 1. I just didn't write it. So if we think about that, we say, hey, what about B sub n? Well, it's going to be 500 times e to the 0.03 times 1/12. 2, okay, good, dorky, to the n minus 1 power, plus all the way down to that last $500 I'm just going to deposit. Okay, so what I'm hoping you look at now is you realize, hey, wait a minute, this is actually a pretty special sequence. Let me just write in a few other terms that I didn't show. Like, for example, this might have been 500 e to the 0.03 times 1/12. Plus that last $500. Prior to this would have been in here plus ... 500 times e to the 0.03 times 1/12 squared. Hopefully you see that that's a geometric series. I'm multiplying, every term is getting multiplied by this. So this is geometric. And you can actually identify the important parts of it. For example, something's acting like the first term, and something's acting like the common ratio. All right. So the first term is right here, 500. And the common ratio is the thing that I multiply each term by to get the next term in the sequence. So to go from 500 to the number before it, I must have multiplied by e to the 0.03 times 1/12. And sure enough, if I multiply that by that term again, or that common ratio, I'd land on this term. And I just keep going across. So this is e to the 0.03 to the 1/12 is my common ratio. And I think that makes this problem a little bit tricky, because this common ratio isn't really that nice to look at. So the nice part about that is we know some formulas. For example, we learned that the nth partial sum of a geometric, S sub n, is the first term times 1 minus the common ratio to the n power over 1 minus the common ratio. A. So what can we do now? We could actually just think of our Bn. Our Bn is going to be the same thing, except we know the stuff that's missing. Here's the 500. That's going to be my first term. And we know our common ratio. Now just for this, make this a little easier to look at, if you estimate this in a calculator, you get about 1.0025. That's how I'm going to write that. So 1 minus 1.0025 to the n over 1 minus 1.0025. Once you have this, you can answer all kinds of questions. Right? I could say to you, what's the balance of the account in the 7th month? So what's B sub 7? Well, it's going to be 500 times 1 minus 1.0025 to the 7th. Or 1 minus 1.0025. Remember, that would be the balance in the account, given that you showed up at the beginning of the 7th month and deposited $500. So then after you deposited that $500, that's what this would be this week. So this gives us about 3526. Okay. You could ask questions like, what's the balance in the account after 2 years? Now remember, n is representing the number of months, so we have to find b sub 24. So all it would require is that in this formula you change that 7 to a 24, not a 25. If we do that, hold on a second here, we get about 12,351. Okay. We could ask questions like, when's the first time the account goes over a certain amount of money? If you wanted to make, say your goal was to make it to $10,000, how would you do that? Well, that's sort of like solving backwards. So let me show you. So we want $10,000 to equal 500 times 1 minus 1.0025 to the n over 1 minus 1.0025. Whatever that turned out to be, we can solve that. Let's do a little algebra, actually. So most likely I'd probably put this over 1 and maybe multiply like this. Multiply through by that expression if you want, and cancel the denominators. You get 10,000 times 1 minus 1.0025 equals 500 times 1 minus 1.0025 to the n. What can we do now? We could divide, I guess. Divide by 500. Divide by 500. So what do we get here? 20 times 1 minus 1.0025 equals 1 minus 1.0025 to the n. The only term that has a variable in it is right here, so I'd like to get that alone. So I guess I could bring this to the other side, and I'll bring this term to that side. If I do that, I'm going to have 1.0025 to the n equals 1 minus 20 times 1 minus 1.0025. So what we're really looking for, we want to take the log of both sides now. So we'll take the log of this expression and the log of that expression. And we know that the n can come down in front. So the last thing we do is divide by that. Go ahead. Let's finish. So n is going to be the log of 1 minus 20 times the quantity of 1 minus 1.0025 over the log of 1.0025, which is about, right, so we get about 19 and a half months. Now keep in mind what n was. N was measuring months. So 20 months. In the 20th month when I showed up to the bank, I'd expect to have more than $10,000. Here we go. You're given the number 1.1222 forever. And we're supposed to figure out a fraction that's equal to that decimal. All right, so I'll show you a couple ways to handle it, and you'll tell me what you think. All right. So here's one way to do it. I'm going to give this thing a name. I'm going to call it n. Okay? And then I'm going to do the following. I'm going to take n, and I'm going to multiply it by 100. And you're not going to see why I did this yet. If you bear with me for a minute, you will. Now, multiplication by 100 is very easy to do because you just move the decimal over twice, right? So what do we get? We get 12.22222 forever. Okay. So here's where I plan to take advantage of the fact that these 2's go on forever. All these 2's go on forever. All those 2's go on forever. So if we subtract this thing on the bottom, you have 100n minus n will give me 99n. And on the right, we've got 12 minus 0, really. That's just 12. And then we've got this 0.2 minus this 0.1, which is 0.1. And then these 2's would cancel, and so would those, and those, and those, forever. And that's the fun part. See, normally we look at decimals that go on forever and we get kind of annoyed because we know we can't ever really write them down. However, clearly, for every 2 I had on the bottom here, there'd be a 2 on the top to cancel with it, and vice versa. So that means if I continue to subtract forever, those are all just going to go to 0. And why am I happy? Because this equation is something I learned to solve a long time ago. Divide by 99, I get n equals 12.1 over 99. Traditionally, fractions are written with it's just integers on the top and the bottom. So I can get rid of that 0.1 quickly by multiplying by 10 on the top. I have to do that on the bottom as well. So in effect, I've multiplied by 1. I get 121 over 990. And that fraction, when you divide that in your calculator, you get 0.1222222 forever. Let's try and think of this from a geometric series point of view. All right? So what I'm going to do is I'm going to take this 0.12222 forever, and we're going to rewrite it. We're going to write this as 0.1 plus 0.02 plus 0.002 plus 0.0002 forever. Now, as this stands, the way I've written it right now, it's not quite a geometric series. And the reason is, to go from this term to this term, you'd have to multiply by 0.2. But then if I tried to do that again, for example, if I tried to multiply by 0.2 again, I would not get that term. So this doesn't quite look like a geometric series. However, if we're just a little bit clever about things, we can get this to work. Take a look at this. 0.02 plus 0.002 plus 0.0002 forever. If we ask, is this a geometric series, watch what happens. What do you multiply by to go from that term to that? Yep. Times 0.1. And then if you try that again, oh, sorry, wrote that wrong. Let me fix that. Times 0.1. Oh, wow, that works, right? So this 0.1 wasn't making me very happy. I'm just going to put that over here by itself and not worry about it for the time being. I can deal with this. That's geometric. That's an infinite geometric. And we know the sum of an infinite geometric. The sum of an infinite geometric is the first term over 1, or divided by, I should say, 1 minus the common ratio. You can use this, which would end up giving us 0.02 over 1 minus 0.1, which is going to be 0.02 over 0.9. Which if you want, you multiply the top and bottom by 100, you get 2 over 900. Sorry, my bad. Not 900, 90. I think that does it. All right. So our final answer, I'm going to add these two things together. I'm going to have 1/10 plus 2 over 90. Well, we can do that. Common denominator would be 90, I guess, right? This is going to be 9 over 10 plus, 9 over 90 plus 2 over 90 is 11 over 90. Here you go, 11 over 90. Now, here's another way you might have thought of it. You could have remembered that S sub n, the nth partial sum of a geometric, is a times 1 minus r to the n over 1 minus r. So in our case, it would have been 0.02 times 1 minus 0.1 to the n over 1 minus 0.1. And that's S sub n. But then you ask yourself, well, what's n? And what we're really saying is, I want n to go to infinity. I want n to be a really huge number. So I need to think for a minute. If n gets really big, if n goes to infinity, what happens to the decimal 0.1 to the n power? And the answer is it gets close to 0. And you could, just a little bit of thought will tell you why. Watch. Do 0.1 to the 1, you get 0.1. 0.1 squared gives you 0.01. 0.1 cubed gives you 0.001. And 0.1 to the 10th would give you 0.1, 2, 3, 4, 5, 6, 7, 8, 9 with a 1. So you can see, as this exponent gets bigger and bigger, the answer I get is getting closer and closer to 0. So what does that do? It drops this term out. this term goes to 0, and this whole expression reduces to 0.02 times 1 over 1 minus 0.1. That's the same thing we had in the prior problem. Add it back to 0.1, and you'll be fine.